let's look at an interaction regression output. So someone take a stab at interpreting this.
The intercept now represents something different with the interaction involved, or is that still the average amount of barks for small fluffy dogs?
Now the intercept is the average amount of barks for small fluffy dogs. Before, it wasn't quite the average number of barks for small fluffy dogs.
Right. Okay, that makes, because it was within.
And we'll see why. I'll show you why in a second. We'll get an illustration of it when I draw some lines on this plot. But I wanted to make you try to interpret before I draw lines on the plot. I think the lines will help in a minute, though.
So can we focus, like maybe let's focus on the big estimate first?
Sure. What does this one mean?
I was just going to ask, if we're given a data set, so it's not necessarily our data and we can sort of intuitively know what the comparison group is, can we figure, like sort of ascertain what that is by looking at what the manipulations were and what the, so because these variables are size big and fur scruffy, we can sort of just assume that the comparison group is going to be small and fluffy, or is there sort of a better way to do that if it's not our own data set?
Well, yeah, if you weren't familiar with the data, you would want to know what the levels of these factors are ahead of time. So the first thing I would have done is probably look at a table of size. Right, can't do it like that because size is within the data frame DAT. And I would see that there's 85 small and 115 big. And this is an enumeration of the levels of this factor also. So I know that there are two categories, small and big. And I would want to know that before I even start fitting models about it. So once I knew that, then if I ran a model with that factor size, I would be expecting it to be including a dummy variable, an indicator variable based on that factor. And I just know that R prints the name of, by default, the level that it's treating as the value 1, and the other one would be treated as 0 in this default indicator variable.
Would the first line be that big dogs bark less than small dogs when they're fluffy?
Exactly. Yeah.
Oh my God, I'm so, okay. I know that was so simple, but I'm so proud of myself. I get thrown off by the, I get thrown off by the comparison things, like which one I'm supposed to choose. Okay.
Yeah, this is, that's exactly right. Yeah. It's a simple effect of size at the comparison category for fur. So big dogs on average are barking 16 fewer times than the small dogs when they have fluffy fur. Or you could say the big fluffy dogs are barking 16 fewer times than the small fluffy dogs are.
Wait, sorry, could you say that again? How is fluffy part of it?
This is the difference between big and small in the fluffy category. Or you could say big fluffy dogs are barking 16 times fewer than small fluffy dogs.
Okay. And then the scruffy, the fur category is scruffy dogs in the small category?
You mean this row?
Yeah.
What do you think it means?
Okay, so if the first one is big dogs in the fluffy category, then would that be scruffy dogs in the small category? Because that's...
Well, scruffy dogs in the small category compared to who?
Compared to scruffy dogs in the big category.
Not quite. Negative 39 is the difference between the scruffy and the fluffy dogs. But it's restricted to a particular category because these are estimated in the presence of an interaction. Yeah.
Right. Okay. So sorry. Is the category it's restricted to small dogs?
Yes. Yes.
Okay. Cool. Thank you.
So this is like saying small scruffy dogs bark 39 times less than small fluffy dogs.
Okay.
And if I'm looking over at this picture, that is this difference, right? This negative 39 is if we were in the middle of this blue cluster here, and we were asking how far down do we have to go to get to the middle of this red cluster here. And this negative 16 is like if we were in the middle of this blue cluster here. And we want to ask how far down do we have to go to get to the middle of this blue cluster here.
Okay, that makes a lot of sense.
How about the intercept? Well, we already talked about that, right? That's the average Borks from small fluffy dogs in this data set. So that's this blue cluster here, the average of this one, which makes sense, right? 59.6, that sounds about right for what this cluster's position appears to be visually. So then the interaction term, I think it's sometimes helpful to think about it for a second. Although in practice, you can get away without having to wrap your head around the numeric value of an interaction term that often. And there are many ways to think about it. Here's one. Suppose I'm imagining, I'm using this small fluffy dogs as my reference category, and I've already learned that the big dogs are 16 points lower within the fluffy category. So, right, so I've learned that this blue cluster is down 16 from where I'm at. And this red cluster over here is down 39. In other words, the small scruffy dogs, I would go down to get from small fluffy to small scruffy, I need to go down 39. So from my reference category of small fluffy dogs, scruffy appears to bring me down 39, and big appears to bring me down 16. That was these two terms, right? So let's say I wanted to guess the location of the big scruffy dogs. If all I knew was this stuff, then I might be tempted to guess that I have to go down 39 and down another 16, and I would be way down here. If I was just adding together the simple effects of the size and the fur, then I would end up down here, and I would be wrong in estimating where the big scruffy dogs are. How wrong would I be? Well, I would have to go up another 14.6 points to get the right answer. So if I treated these as additive effects, I would have to add in this much in order to get the right answer. That's one way of thinking about it. Not usually the most intuitive way for everyone, but one that I thought I would bring up. Another way to think about it is, let's suppose I'm focusing on this. I've learned that the slope associated with the size variable is -16 for the fluffy dogs. So the difference between small and big is 16 for the fluffy dogs. How much different would that slope be for the scruffy dogs? So I know that big dogs are borking 16 points less when I'm focusing on fluffy dogs only, but what if I was to focus on scruffy dogs only? How much less would the big dogs bork than the small dogs then? Well, it would change this value by 14.6. So the big dogs would only be borking around 2 points less.
So you always add that, right? Like that's how you get to realizing it's less, because you're adding it to a negative.
To this number, yes. Yeah.
Okay.
If you add these two numbers together, the 16 and the 14, the -16 and the 14.6, then that is the slope of the size variable for the scruffy dog.
And that's actually how I normally think about interactions anyway. Like it's a difference of differences. So a difference of the slope, and then that makes sense. The other way made sense to me too. But in terms of how I think about,
this is exactly what it is. And you'll find that certain subfields like to talk about difference in differences analysis as though it's a different thing from testing an interaction, and it's not. That's all we're doing here. We are calculating the difference between the big small difference for fluffy dogs and the big small difference for scruffy dogs. And that difference between those two differences is 14.6. That's how different the effect of size is, depending on whether you're talking about fluffy or scruffy.
And then is it the same thing for scruffy, fluffy, like the difference between scruffy, fluffy for small dog, and then that difference is 14 less for big dog?
Yeah, well, yeah, definitely, right. That's one way to, so the difference between fluffy and scruffy is negative 38.7 when we're talking about small dogs. And if we wanted to talk about big dogs, we would have to add the 14.6 to it. And so the difference for big dogs would be negative 38.7 plus 14.6, which would mean that the slope would be weaker. The slope would be more positive by 14.6 points, right? Which brings it closer to 0 in this case.
Well, that makes sense. That helps a lot.
So then let's say I change the reference category for fur to scruffy, and I get this result. What changed? Here was the, well, I guess I have a lot of stuff. Here was the output before. And I noticed that the big dogs barked 16 times less than the small dogs. Now I've changed the reference category to scruffy. What's the result?
So for the fluffy, so when you're comparing fluffy and scruffy, that the sign just changed, right?
This one. Yes, the sign just changed. Yep.
Because you only changed the comparison for the fur variable.
Yeah.
So now the first line, or under the intercept, big dogs bark, well, it's not significant, but if it was, big dogs would bark less than small dogs in the scruffy condition. So when they're scruffy. So scruffy, well, it's not significant, but I still want to try and say it in the direction. Big scruffy dogs bark less than small scruffy dogs.
Yeah. And it not being statistically significant doesn't change that that's the correct interpretation. In this data set, big scruffy dogs are barking 1.6 times less often than small scruffy dogs, right? And then the question that you might be interested in is that difference big enough that we're sure that it's not a coincidence, right? And of course it's not, right? That's what we mean by not statistically significant, that might be an accidental difference rather than a systematic one, but it is in that direction in the data set that we have. And these other two numbers stayed the same, except with the opposite sign. We've already interpreted them.